Hello everyone, I'm Lingman Zhao from Shanghai Jiao Tong University. I'm going to introduce our work, Few-Shot Class-Incremental Learning via Class-Aware Bilateral Distillation. In this paper, we focus on the challenging task of Few-Shot Class-Incremental Learning. In experiments, we reveal that directly applying the traditional knowledge distillation technique is not suitable for Few-Shot Class-Incremental Learning tasks. To solve the above issue, we first propose a class-aware bilateral distillation method by adaptively drawing knowledge from two complementary teachers. Second, we propose a two-branch network where the two branches are well associated by the above distillation module and an attention-based application module. Moreover, the superiority of our method is validated on three popular Few-Shot Class-Incremental Learning datasets. Let's talk more about the Few-Shot Class-Incremental Learning task, which learns new knowledge from few novel class training samples and resists forgetting previously learned old classes. As shown in the figure, the model is trained on a series of incremental sessions, where the base training set in the first session contains sufficient data for base classes. However, compared to traditional class incremental learning tasks, the training sets in the following sessions only contains few training samples. After training in each session, the model is evaluated on test samples from all the seen classes so far. The motivations of this paper are discussed on this page. We find that the vanilla knowledge distillation method is not suitable for the current task. It is because while knowledge distillation is a prevailing regularization technique in traditional class incremental learning tasks, it fails to consider the overfitting risk of novel classes in few-shot settings. In addition, the scarcity of training samples also aggravates the catastrophic forgetting problem. To adapt the powerful knowledge distillation technique for few-shot class incremental learning, we propose a novel distillation algorithm by taking the unique challenge of overfitting into account. We draw knowledge from two complementary teachers. One is the model trained on abundant data from base classes that carries rich general knowledge to ease the overfitting of current novel classes. The other is the updated model from last incremental session that contains the adapted knowledge of previous novel class, which is used for alleviating forgetting. Formally, in our proposed class-aware bilateral distillation, the guidance signal for distillation is an adaptive convex combination of two logics. One is the output from the base branch trained in session 0 to alleviate forgetting, and the other is the output from the novel branch trained in the last session to resist forgetting. Furthermore, the combination coefficient is learned in an end-to-end manner for adaptively controlling the extent of transferred generalizable knowledge from base to novel classes, conditioned on the class-aware semantic similarities. Despite the remarkable classification performance of novel branch trained using our proposed distillation module, it is inevitable to incur base class forgetting due to fine-tuning on novel class training set. To further improve the performance on base classes, an attention-based aggregation module that selectively merges predictions from both base and novel branches is proposed. To enhance discrimination between base and novel classes during the model training, a binary classification loss function is also proposed for producing appropriate attention weights for each class. In experiments, we conduct comparisons with existing methods on three publicly available few-shot class-incremental learning datasets and consistently achieve state-of-the-art performance. For example, we surpassed the second-best approach by 3% for the improvement in the final session and boost the average performance by 1.5% on mini ImageNet by default. With more exemplars stored, we further improved the final result by 1.2% thanks to our distillation module for effectively exploring useful knowledge from the data. When exemplar is unavailable, our flexible framework still surpasses all previous methods due to better novel class adaptation in extreme scenarios. We further provide a detailed analysis of the combination coefficients for our distillation module. From a datasset-wise view, these coefficients shows a positive correlation with the average level of semantic similarities, validating that more general knowledge from base branch should be transferred when base and novel classes are more semantically related. From a class-wise view, the figure shows that the coefficients tends to be a larger value when the novel class is more similar to the base ones, since more generalizable knowledge can be leveraged, which again accords with our intent to design the module. We also provide ablations on the attention weights for aggregation. As shown in the figure, we observe that test samples from base classes induce larger base branch scores to leverage more predictions from base branch, while novel class test samples produce larger novel branch scores as is expected. Moreover, the individual base and novel class accuracy, as well as the harmonic mean in the right part, validates that our aggregation module can better trade off between base and novel class performance. The above superiority of our method is also validated from the view of confusion metrics. Our full method with the proposed distillation module and the proposed aggregation module can obtain a much clearer confusion matrix, confirming the observed performance gaps in experiments. From the view of t-SNE visualization, we find that our proposed distillation module can better adapt to novel classes without severe base knowledge forgetting. Thanks for your watching.